Welcome back to Arxflix. Today, we're diving into an exciting new paper titled World Models. This paper focuses on building generative neural network models to learn spatial and temporal representation in reinforcement learning environments. We'll break down the key concepts and experiments detailed in this research. Here's an illustration from Scott McCloud's Understanding Comics, highlighting the idea of a world model. Like humans, the model creates an internal representation of its environment to make decisions. Humans utilize mental models to navigate their world using abstract representations of high-dimensional sensory inputs. These models predict future sensory states based on current actions. Similarly, artificial agents can benefit from good spatial and temporal representations coupled with predictive models. This framework uses a large RNN-based world model to mimic environments. The training involves recorded observations to create these models, later used to train agents. In this paper, the agent model consists of three main components: vision, V, memory, M, and controller, C. This figure shows the components. The vision model captures and compresses spatial data, the memory model predicts future states, and the controller decides actions based on the representations. The vision model, V, uses a variational autoencoder, VAE, to compress high-dimensional sensory input into a lower-dimensional latent space representation, denoted as Z. Here is the flow diagram of a VAE. The V model's goal is to reduce the complexity of each observed frame into a compact latent vector, Z. The memory model, M, employs a mixture density network RNN, MDNRNN, to predict future latent vectors, approximating the probability distribution of future states. This depicts an RNN with a mixture density network output layer. The MDN predicts the distribution of the next latent vector, SEAT1, conditioned on actions and past states. The controller model, C, is a simple linear model mapping the current latent vector and the RNN's hidden state to action decisions. This linear formula illustrates how the controller maps the concatenated vector of ZT and HT to the action, a T. The full model, V encodes inputs, M predicts future states, and C decides actions to maximize rewards. The researchers tested their model in the car racing V0 environment from OpenAI Gym. The goal was to navigate through randomly generated tracks and achieve high scores. In training, the world model learns representations of frames and predicts the sequence, without reinforcement signals during this phase. Steps involved were collecting data from random policies, training the VAE, modeling the action-conditioned probability distribution with MDNRNN, creating a controller, and optimizing it with evolutionary strategies. Results showed the advantage of combining both the vision and memory model over using just vision, leading to more stable driving and better scores. This video shows that giving the controller access to both ZT and HT improved stability significantly. Their approach was also validated on the VizDoom environment. The agent learned to avoid fireballs shot by enemies based entirely on its hallucinated environment. The agent trained in a hallucinated world was able to effectively transfer its policy to the real VizDoom environment, achieving high scores. This work demonstrates the potential of using generative models to facilitate learning in RL tasks, reducing computational demands on actual environments, and achieving impressive performances through compact, efficient policies. Thanks for joining us on this deep dive into the World Models paper. If you want to explore more, check out the interactive version at World Models, GitHub.io. Don't forget to subscribe for more cutting-edge research summaries here on Arxflix. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.